Greetings, Panthers. It's Dr. Augustine, and believe it or not, we are almost done with section 17.4. This section is a bear. There's a lot to it. We've looked at just what are titrations in general. We've looked at strong acid, strong base titrations and all the 4 different regions within that, how to calculate a theoretical curve. The last 3 videos, it's actually taken 3 videos to explain a weak acid, strong base, or a weak base, strong acid curve. Looked at different regions for that. So this video is going to be sort of a summary of what's gone on and also some points that don't really fit neatly into one nice place. It's kind of a other considerations, I'm calling it. So a couple things, I'm going to use words. I'm not going to use as much calculations on this or hardly any calculations on this, but let's just take a few words to talk about some of these things. So first thing, what if we have a polyprotic acid? So what if we have something like H2SO4, for instance? So H2SO4 has 2 H pluses in it, and therefore when we do a titration curve, we're actually going to get 2 peaks to the titration curve. We're going to get the first peak, which is the first equivalence point, and then we're going to get a second peak for the second equivalence point. So the curve is going to look basically the same, just going to have 2 peaks to them. I'm not going to bother going through a calculation of this entire step. If you can do the last one, you're in good shape. You don't need to worry about how to calculate every step of the theoretical curve. But just recognize, if we have a polyprotic, a diprotic acid in this case, we're going to get 2 peaks. If we have a triprotic acid like H3PO4, phosphoric acid, we're going to end up with 3 peaks. Okay, quick, check that off. We've talked about polyprotic acids. What indicator should we use in a titration? And you may say, well, what difference does it make? We're just going to grab an indicator. Well, it actually depends on the titration curve that you're using. So the one that we use commonly is called phenolphthalein. This is the clear to pink curve, and this is what the colors look like. So the colors actually change with the pH. So if you're very interested, this is what the structure looks like. When it's acidic, it's colorless, and you notice there's this bridging oxygen here. And if you get to a basic pH, then this bond breaks and we end up with a negative, and actually we lose a proton off of this OH, and we end up with negative 2 charge, and the color changes to this bright pink / purple. Now you've seen this before, we've done this reaction before, and this is the pH what the color changes. So it's actually clear, 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 even through 7, 9, and 10. So you might be saying to yourself, hey, wait a minute. We've been using phenolphthalein as our indicator for all of our acid-base titrations in lab, but it doesn't actually change until it's above 7. So how have we been able to do that? Actually, this pH change turns out to be at 8.3. That's where this color change really begins to happen. So you might be asking yourself, how are we able to do that? This is this picture right here is the actual pH curve for phenolphthalein. So the reason why we're able to get away with this is because think about these curves. I'm going to sketch out the strong acid, strong base case. All right, so here's the pH, here's the volume of base. And you should recall that the equivalence point for a strong acid, strong base should be 7. Okay, but we've been using phenolphthalein, so you've done this reaction many times. HCl plus NaOH yields NaCl plus H2O. I mean, that's kind of a super common. You probably did it in high school. You've definitely done it here at High Point. So you might be saying to yourself, well, how am I able to get away with this if this color change doesn't occur until 8.3? The reason why you're able to get away with it is because this curve is so steep here. So for a strong acid, strong base case, we have a really steep curve, and I haven't even drawn it correctly, really. I mean, it's really much steeper than that. So that means, essentially, anything between, say, here and here on the pH curve would be fine if we picked an indicator that changed in that region, because it's such a tiny change in volume. Remember, this is volume here. So the difference between a pH of 7 and 8.3 is almost nothing. So for a strong acid, strong base case, we can really pick any indicator that changes from, let's say, 5 up to, let's say, 9, probably even more than that. But any indicator that changes in this range from 5 to 9, we can get away with because this curve is so steep in this region. And so any indicator we pick along this bar will be fine. The color will change just fine. All right, now you might be saying to yourself, well, wait a minute, there's more indicators than just phenolphthalein. That's the one we've always used. That's true, but there are more indicators. In fact, there's a whole bunch more. So here's a table from your book, table 17.1. This shows different indicators, and there's a whole bunch of different ones, and this shows the pH range where they change color and also what color changes actually occur. So here's our friend phenolphthalein. It actually changes up in the 8 to 9 region, all right? And so for a strong acid, strong base, we can really pick anything from like brome, cresol, green, all the way up through phenolphthalein and maybe even thymolphthalein. Okay, any one of these indicators will work for a strong acid, strong base. But that's not generally true. Okay, we can't use any indicator for any type of reaction. So let's think about the shape and structure of the strong acid, strong base case, which we spent so long talking about. That one goes like this and up like that. And remember, if this is pH 7, here's volume base. Remember, the equivalence point is actually above a pH of 7. So what does that tell us about the type of indicator that we could use for a weak acid, strong base case? What type of indicator could we actually use with that? Well, we can use anything that changes from maybe 7 up to 9 or 10 or something like that. So in other words, we're going to be restricted now to things up here. We can't use just any indicator. We can only pick the ones that change up at 7, 8, 9, 10 kind of pH range. So phenolphthalein still works fine for this, but we can't use some of these ones that change at a low pH. All right, so we're actually limited into what types of indicators we can use. And of course, if you're following my logic here and you remember what happens for the weak base strong acid case, that's going to look something like this. pH is 7. So this is a weak base strong acid, and this is now going to be volume of acid, something like HCl. The equivalence point is going to be less than 7. And so what does that tell us? That tells us we need to pick something down here, maybe say from 7 down to 4 or something like that. So maybe something like this range from 2,4-dinitrophenol up through maybe bromethymol blue. Okay, so depending on our reaction, depending on the pH change of the reaction, we're going to need to pick an indicator which is going to ideally change somewhere in this region of the pH curve. Okay, so a weak base strong acid, a weak acid strong base, we're going to have to use different indicators for this, depending on what it is. Something like methyl red is actually pretty useful because it changes over a wide pH range, goes from this pink color all the way to a yellow color. And depending on where we are, methyl red can actually be used for most types of reactions. Okay, so the last topic I want to tackle here in terms of acid-base titrations, we've talked about polyprotic acid, we've talked about what indicator should you use in the titration. Remember, it depends on the type of titration you're doing. It's going to depend on which indicator you're going to use. The last thing I want to talk about are we can actually use the titration curve to figure out what the pKa is of a weak acid or a weak base. So if you actually just do the experiment, this is the way we can figure out the pKa. In fact, if you ever wondered, how do they know this pKa? How do they know the Ka? It's by doing a titration. So let me walk you through the process for how this is done. All right, so here's our titration curve. And we're going to do a weak acid, strong base case, but you can make the same argument for weak base, strong acid. So again, we have pH on this axis, we've got volume of base added on this axis, and remember it's going to curve up a little bit, get steeper, and go like this. This right here is called the equivalence point, as you know. All right, and we'll make it nice and easy. Let's say this is 40 milliliters of base. And our pH at the equivalence point is going to be more than 7 because this is a weak acid and a strong base. So let's say the pH is 8.5 or something. Okay, so how does that help me? How can I use that to figure out what the pKa of this acid is? So let's think about this reaction, the actual acid-base reaction. So we've got HA, aqueous, plus OH minus, aqueous, yields H2O, liquid, plus A minus. Okay, that's our general chemical reaction. And if we make a mole table, let's say we have an initial number of moles, we have a change. This is not an ice table, it's a mole table, and we have final number of moles. Okay, so I'm going to pick some really easy numbers. Let's just say we start out with 0.1 moles of the HA, of the acid, and at the equivalence point, you realize that we have the exact same number of moles. We have 0 of the conjugate base to begin with. We're going to have 0 of the acid, 0 of the OH minus, and we'll have whatever that number of moles is formed in the product side. Okay? Fantastic, right? Let's take a look at a little bit different situation. What about when we have halfway titrated this? This is called the half equivalence point. So we have the same number of moles, 0.1 moles of the acid, but we have 0.05 moles of the base. And we have 0 of this to start with. So this is going to go down by 0.05. It's the limiting reagent, right? This one's also going to go down by 0.05. This one's going to go up by 0.05. So we're going to have 0.05 moles of the acid, 0 moles of OH minus, and 0.050 moles of the base. Okay. Why is that significant? Okay, so that is the half equivalence point. In other words, halfway. So in this particular drawing, I'm going to say it's at 20 milliliters, halfway. And you notice a couple of things go on at this curve. First of all, the curve is changing slope. It's going from a positive slope here to a negative slope here. So that's called an inflection point. If you remember that in math class, the curve is curving up here and it's curving in a different direction once you pass that point. That's the half equivalence point. The other thing you notice is the equivalence point actually is a change in curvature as well. Okay? So that region of the curve is the buffer region, right? And what did we say in the last video? Any place along the buffer region, you can use the Henderson-Hasselbalch equation. So let's drag out the Henderson-Hasselbalch equation. pH equals pKa plus log number of moles of conjugate base times number of moles of acid, HA. So this is going to be pH equals pKa plus the log of 0.050 divided by 0.050. That's going to equal to 1. So pH equals pKa plus the log of 1, which that is equal to 0. So lo and behold, the pH is equal to the pKa at the half equivalence point. So we can extrapolate over on this curve. And this, if we want to know what's the pKa of my acid, all we need to do is do a titration, find the equivalence point, divide it in half, whatever volume we came out with. If it comes out to 60 milliliters, you go back to the 30 milliliter mark, and then just figure out what the pH was at that point in the curve, and that's your pKa. So that's how you figure out what the pKa is, by actually doing a titration, doing it carefully, measuring the pH as you add volume of base, and you can figure out what the pKa is. Now, a couple of you in this class, some of you might know quite a bit about math, and you realize that at one of these inflection points that we just talked about, the curve, if we took the derivative of this curve, we would actually get a little peak right there. So we can actually do this by taking the derivative, and we're going to get a peak at the pKa, and we're also going to get a peak at the equivalence point. So if we want to get a really accurate number, we can actually take the derivative of the curve as we're taking the measurements, and we can figure out what that half equivalence point is. So this is called the half equivalence point. And at that half equivalence point, we can find the pKa directly from a plot. One more topic to cover, and that is, can we use a titration curve to tell us how strong an acid is or how strong a weak base is? And of course, the answer to this question is yes, or I wouldn't be bothering to do it. So let's drag this out of the way, and I'm just going to sketch a couple of different titration curves. So this, we're going to, again, just because it's easy, we'll do weak acid, strong base titration curves, and we're going to look at a couple different curves depending on a couple of different acids. And let's say they're all the same molarity. Notice they all kind of have the same basic shape to them, but they don't all start at the same place. Remember, this is pH on the y-axis, this is volume base added on the x-axis, and these curves do not start at the same place. If we were to correctly or approximately draw this, we would need the pH around 7 would be here. Okay, so all these guys are going to start at a lower pH than 7, but some of them are really low, maybe around 1, and some of these are up around 6. Okay, so first of all, why is it doing that? Well, do you remember what that first point in the curve is? That was derived by taking a concentration, let's say a certain molarity, and using an ice table to figure out the H3O plus concentration. So immediately this tells you, because this falls somewhere along this graph, increasing numbers, this has to be a stronger acid. I mean, if we use the same concentration, let's say these are all 0.1 molar, and this curve right here is at the bottom, that's telling you that is a stronger acid. Okay, but we just have another tool which we just talked about. Remember the half equivalence point? The half equivalence point tells us the pKa. So at this half equivalence point, this isn't drawn great, but the pKa is decreasing, right? Because this might be a pKa of 2.5, this might be 3.2, this might be 4.5, this might be 5.6 or something like that. So the pKa is dropping, but a smaller pKa is a stronger acid. The pKa is a measure of the acid strength. So as the pKa goes down, the acid strength goes up. We can find that from the half equivalence point. So just from looking at these curves, we can look at these curves and say, this is increasing acid strength as we get on the curves. And I'm going to really quickly sketch this out, but same thing for a weak base. Okay, so this is going to be increasing pKb, and that's going to be a stronger base. Okay, that summarizes, believe it or not, section 17.4 intro.